Okay, everyone as awake as I am right now? Yeah, cool. Okay, I'm gonna try not to put you to sleep because it's really hot. Um, my name is Andreia. I'm the Editor Tools team lead at GitHub. I do GitHub for Unity and GitHub for Visual Studio. This is not what that talk is about. It's about other things that I like to do. I hack on Mono. I'm a Unity developer. I worked at Unity and I worked at Xamarin and Novell, so all of these things are dear to my heart. I just want to do a quick note and say that I love that F# is still a thing that is ongoing because I did this thing. You might or might not be able to see if I can. In 2010, I did this thing. I created a little org called F#, and then I put in some code that made F# run on Mono. And then I just hear people have fun, and it's still going, so that is awesome. Even though I don't do anything with it, it's just great to see. I'm just glad to see it's still there. So that is my very, very small claim to fame. So today we're going to talk about C# in games, and mostly about scripting languages, and particularly C#, but other scripting languages, and why the game environment is different than other scripting languages that you might know. What is a game? Game is a loop, a simulation, where it takes input, it updates state, it renders. Difference between a game and a simulation and an application in general is that the application UI loop usually waits for some external event to kick off and then does something, reacts, while a game is always running and always simulating, even if you don't provide any input, because it's a simulation of something. So it has its own internal state, and it's always, always running, which is a key to why scripting in games is slightly different from other scripting and applications. And the reason why most games engines are in C and C++ is precisely because you need performance to be able to do a game loop that works well. Especially in VR, if you guys have had fun downstairs with the VR headsets. To make people not sick in VR, you need to have at least 60 frames per second of rendering. And that's consistent. You can't go below and up and change. Consistency is important. If you change frame rates, if you take too long updating your game because you're churning data or something, you make people sick. And for instance, if you're playing with an Oculus or a Vive, if the latency, the time between the player moving his head and receiving the photons in his eyes that react to his head movement is more than 20 milliseconds, you'll make people sick. So performance is rather key, even though it might not be, it's not related to graphics. If there's graphics, performance is even more key, but sometimes it's not the graphics that make things slow or fast. It's just this, where you have a simulation that needs to be updated consistently, constantly, over time, and that's the game constraint. So game engines are written in C and C++ because you need to be as fast as possible, and you don't want to have any layers between you and access to the hardware or rendering or doing everything. But pointers are annoying. And the people that are writing game engines might or might not be the people that are writing the game. And the game teams have multiple elements. And giving pointers to someone to code a game with is not conducive to having a stable game. It might crash. So game content is story, is sounds, interactions, writing, mechanics. This is what the game is. This is the content of it. It's not just a text that it has, but all of the mechanics that are written for it and everything else that comprises that game. And all of these things are written by designers. Sound designers, game designers, level designers, technical artists, all of these people who are not programmers, who may or may not be familiar with C and C++ and the problems of, pointers. So this gives rise this problem of you need to have fast iterations, you have to prevent crashes, you have to give tools to designers to create games, but you have to have performance, basically just causes scripting languages to actually naturally appear, because you want to give tools to the designers to create the content without burdening them with details of the engine. And without, it's really annoying when you're trying to make your character move and you're crashing the game engine because the language is not suitable for that specific purpose that you're doing. So the designers, when they're making games, they are creating code. But the code is the data of the game. Like writing a book, the words that you put in is the data of the book. All of it, all of the interactions and the mechanics are the game, but also our code, which gives itself, if you look at a game creation from this perspective, there's a few advantages. Basically, if you treat code as data, you can easily save and restore game state at any point because the code, the logic is saved as data and loaded as data. This is a bit hard to visualize right now, but I will show you examples of what this means. You also can iterate very fast because you're playing around with code and you can experiment very quickly. So, which means games basically are coded with multiple languages. The game engine is running on one language, but then there's other languages that perform different functions around all of these data creation things in the game. So there's data definition languages, which we all know, CSVs, XMLs, JSONs, everything that defines, there's no logic, it's just data. And then there's runtime languages, which ignore the game engine language, are the languages that game developers provide to the designers for them to actually code the game on top of the engine. And on runtime languages, there's kind of three different approaches to how you provide a scripting language for a designer to create a game. You can just compile it to native code. You can have some simplified language that you just make a compiler and you compile it to native code and then you link it to your engine and you run it. Not very doable. You have to make all your tools. You have to make debuggers, all of these things. It's just coming up with a new language from scratch, kind of annoying. You can transpile something. You can take an existing language and then just translate it to C++ or C or whatever language your game engine is running, and then you can just link those files directly and just generating code from other code. It's a literal translation step. It's better, but it still makes development slow because your engine is still tied to whatever that code needs to be generated and then linked or loaded or something. There's a lot of process in that transpilation, and especially debugging is kind of hard because a designer is coding on one language, but what's actually running is a completely different thing. It's a translation that doesn't match. So all of the tools, you would have to build all of them. So over time, game developers and game engine developers have kind of moved to running VMs inside their engines. So the C and C++ runtime of a game engine is the host. He initializes a virtual machine running a language and then provides access to that language to the internals, provides objects back, and just basically, generally, they talk to each other. And we know what .NET is, right? Nice VM. So over time, Java, Lua, even Ruby, if you want to do that, C#, all of these can run in a VM, a sandbox that you can control, that you can expose, that you can give designers, and then you can communicate back to the engine, and then you can control the whole life cycle of this VM. So you can shut it down and reload it and do whatever you want. So when you think about code as data, sometimes the borders get blurred, and this example is an interesting example. This is not C#, but it could have been done with C# because these are languages on top of languages that get interpreted and run in VMs. So at some point, it's layers and layers of things going on. In this case, it's a puzzle script. And I hope this talk is also ideas for you to experiment with different languages and different approaches to scripting in games. PuzzleScript is an interesting language, all text, where there's no ifs. There's just instructions that you provide, that you define in a text file that do actions. So for instance, let's see if this works. Ooh, it works. For instance, here, it's saying that there's a player in a crate, and if the player moves towards the crate, then the consequence is that the crate also moves. So every time the player approaches the crate one position, it automatically moves, which causes this, right? So all of PuzzleScript is a text file with a definition of a level, which literally is a text file. You can see it online. You can look at a game here. Well, you guys can look at it online. I didn't go puzzlescript.net and look at it. It's basically one single text file. Sokoban was made like this. I made a snowman also made like this. This is a data definition language because technically there's no logic, technically. But it's also a runtime language. It has all of the rules of the game in a text file, one text file, with no control symbols that you would identify in traditional languages. So another example. Another example is the Uncharted series made by Naughty Dog. So Naughty Dog is they make games. Uncharted is really cool games. But their team has a background in Lisp. So when they were building their engine, they recognized, like everybody does, that to be able to have the designers independently make games without being tied to the game engine specifications or problems, and having to learn C++ or having to deal with crashes and generally just pulling in a game engine developer just because they want to make some logic in the game, the best thing to do is provide them a separate language that abstracts all of those details away so they can interact directly with the game. And then naturally, apparently things happen naturally because they're Lisp. They make it a little scheme language because they're Lisp people that basically defines event handlers and reactions. So this is how Uncharted is made. A designer goes in and defines scripts, state scripts, and then defines all of the actions and reactions that happen in all of the situations where you have scripts, and if your character moves, and wait for the other character to move in a linear fashion. I emailed the developer that made this talk. The URL is here below. Because I was like, they give this to level designers, people that have never programmed in their lives. And how do people adapt to this? Is Lisp, is Scheme, something that is easy to follow? Because coming from an object-oriented approach or not being in contact with functional languages or Scheme syntax specifically, this still feels weird. But he said that no problems. People have no problem adapting to this. It comes very naturally. They don't think about global state or how to pass data because they're really just, they have continuations. So when they need to pass data off, they have continuations and pass data off. There's no side effects because they have no global state. So the only thing that the designers are doing is in their little sandbox coding events. Which is completely different from what the game engine actually looks like. But as far as designers are concerned, this is just a normal way. This is coding. This is normal. So that was a very interesting insight into how, if you're not used to coding or programming in certain environments, other environments don't seem as alien just because, it's just normal as long as it works. So constraints breed creativity. We have this problem where you need to experiment. Experimentation is key for games. You need to have fast iteration times because you really want to experiment with mechanics. You want to concentrate on building the content of the game, not the engine. But on the other hand, you need performance because otherwise you're going to make someone sick if you're doing VR, or the experience is going to be poor. So this is where scripting languages evolve in the context of games, to bridge this gap and provide tools for people to create the game without killing the performance. So, which brings us to component-based programming. I'm not an expert at defining these language things, so I'm just going to show you what it is, the concept of what it is, so you can understand better how this works. So I'm going to go into Unity. So this is Unity. It's a game development tool. It's a game engine and game development tool, middleware, basically. This is all done in C# with the C++ runtime. So it's Inception, basically. The tool that you're running is C++ hosting mono runtime that's running C#, and this is how your game runs, but it's also how the whole editor is built. When they thought about doing Unity and they wanted to do C++ runtime because performance, but they want to provide a scripting language, so Mono was a good choice. It runs in a lot of platforms. They were not C# developers. They were game developers. They'd never used C# before. So their usage of the language is completely different from what you might expect. They were not constrained by, how C# is supposed to work, or Visual Studio, or anything. Most of this stuff started on the Mac. So their approach to C# was completely different. The first thing they did was, you have an editor. The best thing that you can do for fast iteration and testing is to just run the game in an editor. You can just run it and try out different values and do things, and you have an instant feedback of how things are working. But to do that, code is data. All of this data that you are setting up for your scene and you're experimenting is, speed and numbers and logic and all of these things. All of this information needs to be reset because you're testing it out, right? So, but this is all running C#, and the game is also C#, and it's also running in the editor. So their approach to basically resetting the world every time you enter play mode and play with your game, like this. Every time you enter play mode, because they're a C++ runtime and they're hosting Mono, they kill Mono and restart it. But the editor is also C# and it's also running in the same Mono app domain. So literally every time you either change a file that requires recompilation or you enter play mode, the whole thing goes down and comes back up. You don't notice because the renderer is OpenGL and it's controlled by C++ runtime, which is still running just fine. It's just the scripting engine behind it, Mono, that's going down. Which means every time you enter play mode or touch a file, they literally recreate all of the data in the entire IDE from scratch, from disk. So they serialize all of this, and then it's just loaded up. And they do this in the amount of time that it takes to do that. So that was, for them, completely natural because they're not doing a C# app and running a C# app. They're doing a C++ engine, and they're hosting a VM. So you can totally kill the VM. As long as it still renders and the pixels are still on the screen, nobody's going to notice. So that's different than you would expect from IDE. It's more like every time you hit debug on Visual Studio, it just shuts down and starts it up, but you don't notice. Unity is also, it's all component-based, which means you have a little cube. I have a little cube right here. This cube. This cube, I'm sorry I can't enhance this, but you can download Unity and play around with it. This cube has a bunch of components. All of these are components. And a few of them are the default cube components. And then a bunch of these are scripts. The scripts are the components that define the behavior of this cube. So when you're doing a C# app, you have an entry point and you start it up, and then you load your UI, and your UI reacts to something, and you have a whole architecture, whatever type of architecture you wanted. Here, there's no entry point. There's not even a new. You never use new around here because this is a language on top of a framework, on top of an engine. The framework instantiates things for you. You attach behaviors to things, and they will be created at the appropriate time when circumstances dictate that component should be activated. Which means your scripts suddenly look like this. So this is a little script that is attached to a little ball. I have a ball. There's a ball somewhere. There's a ball here. It's disabled, so you can't see it. I can enable it. There's a little ball. And the little ball has a little script right there, right here. I just dragged the C# file to the ball, and it attached the script. And then when the game runs, the engine will call start, and you do things on start. Notice that these methods are private, and that there's no overrides and no inheritances. That's because it's a C++ engine. It controls mono. It doesn't have to define inheritance or even interfaces to know what to call. They simply scan every single class looking for methods that vaguely look like what they might call, and then just call them, which means visibility doesn't really matter. Nothing matters much here. There's no namespace declaration because there's no place to put these things. They're just scripts that are attached. You don't create them, you don't reference them, you just attach them to things, and then you reference each other by just basically defining fields which magically pop up in the inspector, and then you can drag things onto it, because all of these things are components that can be dragged and referenced to each other. And the script, a C# script, is just another component that has a task, that scripts something. So this one is just creating a little texture for the ball and making a color for the ball, and then running a sound when the ball is created and destroyed. You can have, this means that when you're defining behaviors, so you want the ball to rotate, and you want a ball to bounce, and you want to put some color, and you want to make a sound whenever the ball does something. You can put this all in one script, or you can put it in 10 scripts. It doesn't really matter, because you can have one script, the only thing it does is bounce, or another script, the only thing it does is whatever you want to do. This is component-based programming at its kind of edge, like extreme. You're not even thinking about how to create a component-based system and then attaching things to it. It's just like the framework just gives it to you. This allows for you to just quickly script your game, enable and disable behaviors. If you want to test out different behaviors of something, you can just enable them and disable. So for instance, I have this object that has 2 scripts attached. There are 2 different approaches to generating a ton of balls on screen that I have. And I can test out each of them by enabling and disabling. When I run the game, one runs or the other runs. These properties that are here, like these things, are defined in the script as public fields. And it will just see that it's a public field called ball prefab. So it will just call a public field ball prefab and kindly put spaces, because as long as you follow the casing, it will just magically do this for you. And you set defaults in the script, but then you change the data here because you're trying it out. You're running it, and you want to change to see how the behavior changed. So you try these things out, and when you're satisfied, you just leave them, because that data is now serialized, because it's your logic, but it's also your data that you need to load. It's serialized to disk separately. So when your game runs, that's the data that's going to be used. So so that's component-based programming, which is surprisingly powerful when it comes to scripting games and giving people the tools to script. As you can see, if you're a C# developer, there's the skills transfer, of course, because you know the language, but understanding what's happening and how is this created, like how is this object suddenly existing? Or like I have multiple copies of it, how do I have multiple copies? What is my entry point? How do I start? Is something that is a completely different concept in these types of systems, but surprisingly very, very efficient at just creating logic and creating behaviors and scripting things. That brings us to data-driven design. So this is an offshoot of the problem of handling data performantly, having performance in your game engine. When you're running in a phone that is going to run out battery, if you are in a loop constantly doing things or allocating too much memory. It is a problem when you have a GC that decides to collect 1,000 objects that you created in the middle of a key action, so the thing freezes for 10 milliseconds. As I said before, if you have a latency of more than 20 milliseconds when you have a VR headset, you're going to be sick. If the GC happens at the wrong time, it's going to make you sick. So suddenly, you have a problem with your data. You have a problem with the performance. How do you define and control when these things happen, when a GC collection happens, or how many objects do you have on screen, in order to actually achieve the performance you need without making people sick, but not, not going back into C++ and scripting things. So this is Factorio. If anyone who's played Factorio? So Factorio is, like I said, this is not all about graphics. Factorio is an interesting simulation of you're in an alien planet and making a little base for yourself and automating a lot of things. Every single object in this screen, this is rather dark, I'm not sure if you can see it, but there's things moving. Every single thing in this screen is a separate entity that has its own behavior and moving around on the screen. Every single one of these. And there's a lot of them. And this is like a zoomed-in version of Factorio because you can zoom out and see a whole lot more. The amount of objects on screen that are moving right now is ridiculous. And to maintain the 60 frames per second that they have, you have to, the entire loop of simulating the position of every single one of these objects and then rendering them on screen and updating the time and the input of the player has to run in 16 milliseconds. That's 60 frames per second. If you go 90, it's 11. And that's what it's doing here. And there's way more objects here. They could have way more objects. So when you have these constraints of performance and handling all of this data, you start to think about data as the driver for the design of your code. I'm not sure how much time do I have? OK, cool. So suddenly, I'm just going to do a little demo here. So I have this little silly thing that I've been hacking around since yesterday, way too long, where I just generate balls, and they fall. And there goes the frame rate. Because I'm doing this in not a data-driven design. So every time I hit the key, I just generate 100 balls, and those are all of them that are getting generated. I'm actually destroying them as they move off screen. So I wouldn't, otherwise I would kill Unity very, very quickly. So this is doable. I mean, like now it's responding again, and I can do a few more balls, and then it's gonna, run out of memory at some point. And the GC is gonna kick in as I'm doing this because it has to clear all of these things. If you're allocating classes, if it's structs, there's no GC, which is another thing that people often use for games. But it's a very intensive process. So what you start doing with data-driven design is that you think of the data not as I'm going to iterate through all of these objects, and then I'm going to check which flag is true, and then I'm going to draw that one to screen. Otherwise, I'm going to ignore it. Instead, you invert it, and you think of the whole logic as more of a data table. where you go like, I have a bunch of arrays. So I have one array for the inactive objects, I have another array for the active objects. All of your conditions, every if in your code becomes an array, a table, a data structure. And then what you're doing at that loop that needs to run in 11 or 16 milliseconds is just iterating through these arrays, right? And you pre-allocate them because you kind of know how many you can put on screen, because you kind of know that if you put too many, the performance is going to go down. So you know your boundaries of your data. You know where you want to run them, how you want to run them. And you build your code around it. So now you have a fixed arrays of X objects that you know are going to be on screen. And then you have multiple arrays, each one of them representing different views into your data. So when you're rendering and iterating and updating, you're not going through all of them. You're only going through the ones that you actually need. So I have a little pool of balls that I've pre-allocated, and I know that that's my pool, basically. And when I'm drawing them on screen, instead of just creating balls over and over and over again, I will just grab from the pool with a fixed array and just iterate through all of them. Which means I can still, make things really, really slow. But I can also draw way more balls on the screen. It recovers faster. This one was the previous example was like 100 balls that I was generating. Here I'm generating 150. And as you can see, they're all there. I'm pre-allocating them. That means there's no GC hitting at the wrong time because there's nothing to collect. I'm just hiding and showing objects. So my point in all of this is that, let's go back to, so my point in all of this is that C# scripting languages in games are more than just the language that they represent. You can twist and turn a language into a specific domain that you want to use it in, that you want to use it as a tool for very specific purposes, which is what Unity is doing here. Other interesting things that you can explore, like F# kit, so you run F# in Unity, and you can do functional programming, no side effects, which is amazing for games, because you can give it to designers, and they won't blow up the engine. Puzzle script I talked about. There's a language series on YouTube from Jonathan Blow, who is a game developer, has never worked in language design, has not worked in C#. He's only done games, and he's making his own language. And when you watch it, you can see his approach to languages, and he's picking up all of these concepts from language designers. He's not an academic in that sense, but he approaches it in the way where this needs to be performant but optimal for scripting, and in combining the best. So it has a lot of interesting concepts that you would not normally see in languages because of the way that we usually approach languages in general in C#. And visual scripting tools, component-based programming also gives rise to that. With that, I will leave it in the talk. And I hope it was a quick glimpse at what C# and game scripting can be. I hope you had fun and not fell asleep too much. Everybody's alive? Okay, I'm done.